All right, these are just some guided notes on page 95. What we're going to do is use what we've learned about motion graphs and position, velocity, and acceleration to derive what are called the kinematic equations for constant acceleration. And so you've probably may remember them from freshman year as some of your physics teachers may have called them the big four. We're actually just going to use 3 of them, and we'll see here graphically where they come from, okay? So what we have here is, it says, suppose an object starts at x equals 1 meter. So here's position, or x, and it starts at x equals 1, so that's actually labeled for us already, with a velocity of 1 meter per second. So let's label some velocities on here. 1, 2, 3, 4, 5, 6 might be good enough. And so it starts at 1 meter per second, so there will be our time t equals 0, and then there's 1, 2, 3 seconds. So here's our time axis for all these graphs. And it says it has a constant acceleration of 2 meters per second squared. So let's label in some accelerations. That will be enough. There's our acceleration axis, there's our time axis. And it says it's constant acceleration of 2 meters per second squared, so that's just going to stay at 2 the whole time. That's easy. So we're just going to look at the first 3 seconds, apparently. First 3 seconds of motion. So let's go to the velocity graph. Well, a couple ways to see it. If we're accelerating at 2 meters per second every second, then the velocity should climb by 2 as each second goes by. And so after 1 second, we need to climb by 2 units. You could also see that by looking at the area under the graph. So notice the area under that first bit is 2, and then another 2, and then another 2. So we climb up to here. And so as each second goes by, we're just going to go up by 2. So there's our velocity increasing monotonically at a constant rate. Okay, it's increasing linearly. So cool, we use the area under the curve to get the velocity graph. Now we're going to get the position plot, and we have to continue to use the area, okay? And so what we can do is use the area under the graph. So during the first second, you really can just count boxes here since each box is 1 by 1. So it looks like we have 1 here, and then this together is going to be an area of 1. Okay, if you went with the triangle, half the base times the height, 1 times 2 would be 2, and then half of that would be another 1. So this is 1 and that's 1, so that's a net gain of 2. And so we need to go up. We need to go up 2 units from where we are. So it looks like we start at 1, and we need to go up to 3. So there we are at 3. And then let's get the next one. So we can just count boxes again. 1, 2, 3, and then this guy's going to give you a 4th. So the area under the curve for this section, the next second, is going to be 4. So we need to climb up another 4 from where we are. So if we were at 3, we're going to have to go up to 7. So now after that next second, 1, 2, 3, we're up here at 7. So let's label that. And you can see we're starting to build up this curve. And then finally, we can get between 2 and 3 seconds. 1, 2, 3, 4, 5, and then that's going to give you a 6th. So we have to add 6 units to the 7 where we already are, and that's going to take us up to 13. So after the 3 seconds, we're going to be up here. And so finally, we can get our curve in here, which is going to be like a parabola. So there's a very specific case, okay? And then, I don't know, for completeness, maybe we don't need this, but I'll just say here we were over 3 and up 13. Oh, it says be sure to label the final values. So here we were over 3 and up 7. And, well, here the final value is 2. I'm not going to bother. All right, so that is constant acceleration. The acceleration was constant, so the velocity grows linearly, and the position grows quadratically. So now what we're going to do is look at a very general case. So this is very powerful because when you look at something general, you can apply it in a number of situations. So now it just says, now suppose the object starts at position x initial with a velocity of v initial, okay? And here's the one little restriction, is it has an acceleration, but the acceleration is constant. So what's going to happen is this acceleration is just going to be called a, right? So the acceleration axis is there, but the specific acceleration it has is just going to be a, and it's going to be constant, like this. Okay, and then maybe at time t it quits doing that, let's just say. So we're just going to see if it has this arbitrary acceleration for an arbitrary time. Well, if you look at what we did up above, to get the velocity curve from the acceleration curve, we had to find the area. And so the area of this box is going to be, well, a times t, because this side is length a and this side's t. So the area here is at. Well, what do you do with that area? That's how much you add to your starting value, like we did the last time. Well, so what we need to do is, well, we start at v initial, and then by the time t goes by, we need to not only be there, but we need to be up at from there. So this gap here needs to be at. And so that's the velocity where we end up. So we end up with a final velocity up here. Well, how high is that? You can say v final is, well, you have to go up by v initial to get here, and then you have to go up another at. So v initial plus at. Okay, so that should bring back some memories. That is going to be your final velocity if you have a constant acceleration. And so here we've done that. Now what we need to do is go get the position graph. And so it's the same story where the area under the velocity curve will give you the change in position. So let's do that also. And so we need to find the area under this thing, but you notice it's got two shapes. It's got a rectangle with a triangle on top. So the area of this one, it's just a rectangle. So that's going to be v initial times t is its area. Here we got ourselves a triangle. So in here, it's going to be half the base times the height. So it's 1/2 of a base of t times a height at, which is going to give you 1/2 at squared. So already it's probably starting to bring back memories. So the total area of this thing is v initial t plus 1/2 at squared as the area. So what we need to do is add that area to wherever we started. Well, we started at some x initial. So from there, we need to go up by a certain amount. Well, that's the sum of these two things. So we need to go up by v initial t plus 1/2 at squared. And then that will get us to our final position, which we can call, say, x final. So that gets us up here, right? That will grow like parabolically from there. Okay, so what we find out, though, more importantly, what I'm really trying to build up here is we have x final. Like, how high are we here? Well, we have to go up x initial first. Then we have to go up another v initial t plus 1/2 at squared. Okay, so this thing, depending on how the teacher presented it, this is sometimes presented as one of the, I think what Mr. Ziegler called Big Four. My style with this is, what I like to do is really just talk about kind of the change in position. So if I bring the x initial over to the other side and just do x final minus x initial, which is, of course, delta x, that's just going to be equal to, well, the terms that are left. So 1/2 at squared plus v initial t. So that is another one of the so-called kinematic equations. And then the final one, which I'm not going to bother to grind through the algebra, and I don't think I'll make you do it either. But it turns out if you eliminate t from these equations, so for example, if you just solve this one for t equals v final minus v initial over a. If you just solve for t and then substitute it in here so as to eliminate t as a variable, okay, so you just get everything in terms of other variables, together, these two equations through algebra, okay, which I'm not going to make you do right now, together, so here I'm just going to write the word algebra. Call me lazy if you want, but you'll eventually find out that v final squared minus v initial squared is 2a delta x. Okay, so that is a third very, very useful kinematic equation that is actually not, it's not new or really independent of these. You can actually just derive them from these two. And that's why when you were freshmen, there were sometimes people would find more than one way to solve the problem. That's because this set of equations you were using, they're frankly not actually independent of each other. So really you just need two of the three and you can get the others. So these things are worth a box and some stars. We are going to spend some time I know you've used them before because you couldn't have done some freshman physics without using them, but we need to do just enough with these so that we kind of get back up to speed. So we're going to spend some time in class working on a set of problems that really just use these equations. The take-home message here with these is do not use these if the acceleration isn't constant. So my skull and crossbones like announcement to you here, so I'm going to even put it in the notes. Okay, so these, realize that the way we set this up is these are only valid for constant acceleration. Sorry, my handwriting gets messier at the bottom of a page like this. For constant acceleration. Okay, triple exclamation point. Okay, so you don't want to use these if the acceleration is not constant. Just as one quick example of when something like that would pop up where they try to mess with you on the AP is if they give you an acceleration, like acceleration as a function of time is 3t. Okay, a huge mistake that somebody might make is they'll say, oh, my change in position, they'll say, oh, I know a formula. It goes like 1/2 AT squared, and then they'll just try to plug in the A for this. Do not do that because this acceleration is not constant. What you should do, right, is integrate this thing. So, you know, what really should we get for x as a function of time? Well, first let's get the velocity as a function of time by integrating, okay? That's going to be, if that goes like t, your velocity must go like t squared. And then this is going to have to go like 3/2. Right, so 3/2 t squared plus a constant, plus your initial velocity. Okay, so plus the constant. And then if you want to get x of t, you've got to integrate this one. So then this is going to go like t cubed. And so then this is going to be like, what, 3/6 or 1/2, right? 1/2 t cubed plus v initial t plus a constant, which will actually be your initial position. So this set of equations would be valid kinematic equations for acceleration that's growing linearly with time, okay? Notice we don't get like 1/2 acceleration t squared at the beginning here. So you really do get the wrong set of equations if you if you try to blindly use these constant acceleration equations in cases when it isn't, you'll mess up. So just my little warning to you. All right, enough of that. Let's start playing around with these things to get back up to speed with using them.